Hello everyone, I Meghamala from EC department IARE, and I'm here to discuss about the modeling levels, modeling styles in Verilog. So before I go forward, let me recapitulate the previous class. So in the previous class, we have discussed how a Verilog acts. In the previous class, we have discussed about the concurrency, synthesis, simulation, system task, and module concept. So, it is just a recapitulation. So, what is a concurrency? Concurrency is all about that video. We have discussed that the voltages and currents in the digital circuits can be modified simultaneously. Okay, so it's not like one after the other, but simultaneously the variations or the changes can be done using concurrency concept. And coming to the synthesis and simulation, we have discussed a basic synthesis and the simulation part. We have discussed the synthesis and simulation based on different syntaxes. Okay, the syntaxes could be of test bench and the basic module syntax. Next, coming to the system task. In the system task, we have discussed about the categories based on the delays and based on the timings and also based on the transfer of data between one register to the another register. These are the different categories where the task has been performed between the modules. And coming to the module concept. In this module concept, we have discussed what is a module, a circuit diagram, what consists of a module. So it consists of this is a module. If it is a module, it consists of the input ports, it consists of the output ports. Okay, so the input ports is nothing but the enter of the input terminals, and the output port is the exit of the output terminals, and also it has in-out ports. Okay, for example, the module input has A and B, the output will be X and Y, and the in-out will be P, Q. So, for this particular module, there is a syntax to be followed. So, that syntax we have discussed: module, the name of the module. For example, I am considering AND gate. Okay, and the ports. Port list. This port list consists of input port, output ports, and in-out ports. Okay, so this input ports, these are we just declare the input ports, output ports, and in-out ports in this port list, and followed by some statements, statement 1 and 2. And if you have more than 2 statements, the statements will be declared over here in the statement. And at the last, we are ending up the syntax with the end module. So, this is the exit of the syntax. This is declaring as end module. So, we start with the module and we end up with the end module, and we declare the module name of the digital circuits along with the ports. And here, before the end module, we have a functional description. Functional description. This functional description could be of gate level, behavioral level, or circuit level. Okay, these are the 3 functional description which is present in the Verilog. When HDL acts as a Verilog, all these three functional descriptions can be used. We can use either gate level, we can use either behavioral level, or else we can use either circuit level. Okay, so in depth also we have discussed gate level, behavioral level and circuit level, but today's topic is about the module modeling styles. We will discuss in depth what is a behavioral, what is a data flow, what is a gate level and what is a switch level in detail. So this is all about the last session that we have discussed. It is a recapitulation session for some time. So this is a recapitulation for the last session. Coming to today's topic, it is module modeling styles. So here we have different modeling styles in order to represent the module. The first one is behavioral or the algorithmic level. The second is the data flow. The third is the gate level. And the final one is a switch level. Switch level is also called as the circuit level. So in this behavioral level, we had discussed a few things in the past, and also today we are going to discuss in depth what is this behavioral or algorithmic level. Coming to the data flow, in this data flow, we will be representing the data pertaining to the module. Okay. And coming to the gate level, we will be discussing what are the gates, what are the different circuits, different gates that we are introducing, that we are representing in this particular module. And coming to the switch level or the circuit level, the complete categorization of a circuit will be discussed in this switch level. Okay, going ahead. Coming to the behavioral modeling, behavioral level or behavior model. So what is this behavioral model? Behavioral level is, this level describes a system by concurrent algorithms. As I said you, the another name for behavioral is algorithm level, algorithmic level. So this level, it helps us to describe the concurrent algorithms. As I said you, in the previous session, we have discussed about the concurrency. That means what? The output can be achieved concurrently. That means simultaneously. It cannot be achieved one after the other, but simultaneously we can alter the inputs and the outputs in order to obtain the perfect output. So this level describes a system by concurrent algorithms. That is a behavioral model, behavioral level. And each algorithm itself is a sequential. As we are achieving the concurrency, each algorithm is a sequential, and it means it consists of set of instructions that are executed one after the other. So here you cannot see the redundancy, but we can achieve a sequential model of executing the algorithms one after the other. And also this behavioral level consists of functions, it consists of tasks, it also has the always blocks are the main elements. These are the main elements that we can see in the behavioral level. Our functions are the tasks that is to be performed based on the time, based on the delay and based on the transfer. Okay. And also we have the key elements that we can observe in this behavioral level is always blocks. Next, there is no regard to the structural realization of the design. As we are discussing about the behavioral level, there is nowhere we can see the structural modifications of the circuit in this particular behavioral level. So this is a simple behavioral model. As I said you, the key element that we can observe here is always. So using the always block, we see the syntax which is followed with the always in the behavioral model. So always blocks, using the always block, always waiting for a change to a trigger circuit. In order to trigger a circuit, in order to go from one particular block to the another particular block, the always there is a change in order to go from one to other. In order to go this, we have to wait, always waiting for a change to trigger a circuit, trigger a signal, that is, then executes the body. So after changing from one signal to another signal, then there we see the execution of a particular task, for execution of a body. So here if you observe the syntax, we have a module and gate. So module is a keyword and gate is a name of the circuit, name of the digital circuit. So module is a keyword that we are using, and the AND gate is a name of a particular device, digital device. And here these are nothing but the port list. So as I said you before, this port list consists of input ports, output ports and in-out ports. So input ports, first of all, in the declaration of port list, we will be declaring the output ports first. Okay, in the port list, I am repeating this once again. In the port list, we will be representing the output ports first and then followed with the input ports. The output ports are representing with out and input ports are representing with in1 and in2. Why? Because here we are considering a AND gate. AND gate consists of two inputs A and B, or else input 1, input 2, and the output we are representing with out. So first in the port list representation, we have to represent the output port first. So out, comma, and then goes to the input port, input 1 and input 2. And coming to the statements, here the declaration of the ports will be seen in the coming steps. That is, input ports in1 and in2 and output ports is out. And coming to the registered out. Registered out is nothing but, here in this Verilog syntax, in the Verilog register, these are the registers are needed to assignment in always blocks. So in the always blocks, always the registers are needed to store the information, to store the data. The Verilog register is needed. Okay, so that is the reason we are representing registered out. The information will be stored in this particular register. Already these registers are by default, by default they are observed, or else they are maintained in the Verilog. So input in1, in2 and output out and the register out. Coming to, and then here we see the always at the rate in1 or in2 begin, and out is equals to in1 and in2. As we are representing the AND gate here, so as it is a behavioral model of representation, in the syntax we have to represent always at the rate in1 and in2 begin. So here this specifies when the block is executed, that is triggered by the signal. So here we are executing the AND gate. So that has to be triggered by the signal, from the input signal to output signal, that it has to get triggered. So that's the reason we are specifying always at the rate in1, in2 begin, and the output here is in1 and in2. As it is an AND gate, the output we are representing as out is equals to in1 and in2. And there you end the sentences, and finally we are terminating the program with the end module. So this is about how we are representing the always block in a particular behavioral level syntax. This is the representations of the always block in the behavioral level syntax. Coming to the register transfer level, or else the data flow. What is this register transfer level? So this register transfer level, it specifies the characteristics of a circuit by operations and transfer of data between the registers. So as the name indicates, register transfer level. The register transfer level is nothing but the transfer of data. The transfer of data can be seen between the registers. So it is specified using RTL, the designs using the register transfer level which specify the characteristics of a circuit. We can specify the characteristics of a circuit. For example, in the previous example, I have considered the AND gate. Okay, so this AND gate, the characteristics of this AND gate can be specified using RTL. For example, I am considering a multiplexer. What is a multiplexer? Multiplexer is nothing but many input, single output. Okay, so we have 2 by 1 mux, 4 by 1 mux, 8 by 1 mux, 16 by 1 mux, and so on. 61 by mux. Many input we see, but single output we observe at the output of multiplexer. So in this multiplexer, we could see some registers to store the data, isn't it? So when we are storing some information in the register, sometimes there is a possibility of transferring the data between the registers. So that can be carried out using this register transfer level or data flow. We can see the other name for RTL, or else we can call the RTL as the data flow. Okay, next, an explicit clock is used because RTL design contains exact timing possibility. As I said you, the transfer of information or else the transfer of data can be carried out from one register to another register. So we see a clock is used. That means for 1 nanosecond, the data from register R1 to be transferred to register R2 within 1 nanosecond. Or else we see some delays. Okay, that delays could be of different types, different categories. Again, they are categorized into different types. So the explicit clock is used in order to transfer the RTL, in order to transfer the data from one register to the another register. Next, operations are scheduled to occur at certain times. So here in this, the operations are scheduled already. They are scheduled at different time intervals. In that particular timings, only we can see the transfer of data from the one register to the other registers can be carried out. So already the operations are scheduled to occur at certain times. At different intervals of time, the scheduling of the operations have been observed in this RTL or else data flow. Coming to the modern definition of RTL code. The modern definition of the register transfer level. The register transfer level is any code that is synthesizable is called RTL code. So here in this particular RTL code is nothing but any code that can be easily synthesizable. Coming to the data flow modeling. So what is this data flow modeling is talking about? This data flow modeling is about the continuous assignment statement is used. In this data flow model, we see the continuous assignment statement. This is an important point to remember. We see in data flow modeling, continuous assignment statement is used. And also the keyword assign is used followed by equals to. The second important point to be remembered is we use a keyword assign is used, and that keyword assign, that means assign is followed with equals to symbol. And the third is most common operator types. Here in this particular table, you could see there are the different common operator types. See, these are the operator types. We have arithmetic, we have bitwise operation, we have shift operation, concatenation and conditional. These are the different operator types and followed with the operator symbols. So each and every in this arithmetic operators, we have the symbols. That is multiply, divide, multiply with star, divide, add and subtract. Already I think you might have well known about all these operators. In the previous classes or in the previous semester, you might have been studied. These are the basic things. Next, number of operands. So what are these operands? So in order to multiply, the two operands are needed, A into B. to divide A slash B. So the number of operands are, for multiply we need 2 operands, for divide, add and subtract we need 2 operands. Coming to the bitwise logical. What is this bitwise logical? Here we have bitwise negation representing with like this, and bitwise and, bitwise or, XOR, XNOR. So for this particular, in order to perform this bitwise logical operations, we need the operands for bitwise and we need only one. As I said you, like this. Bitwise negation A, bitwise negation B. So only one operand is needed. One operand is needed, but the rest of the bitwise logical operations, 2 operands can be needed. And coming to the shift, for this shift we have 2 operands, shift right representing like this and shift left representing towards the left, and the operands, the number of operands that can be needed is 2. That is A shift right B, A shift left B. And coming to the concatenation, concatenation is nothing but any number in the flower braces A with B. Concatenate, adding up A with B. Okay, so any number. And conditional, for this conditional we have the maximum number of operands is to be considered is 3. So in order to write a data flow structure, we have to, this is a procedure actually to be followed, and these are the common operator types and the operands which are to be considered. First one is continuous assignment statement is used. The second one is keyword assign is followed with the symbol equals to, and these are the few common operator types. Example. In this particular example, we see, I said you continue, okay, coming to these examples, we have assign, first one, x is equals to a plus b. Okay, adding up, we are adding a plus b. Assign y is equals to negation of x. That is, negation is nothing but the complement, x complement. And next one is assign y is equals to a and b. And is nothing but a, we represent the operand as a dot b, or and a and b representing with plus, and x greater than or equals to 1 representing with the shift right x by 1. If for suppose x less than 1, it is shift left by 1. And concatenation y is equals to b comma c. So here we are concatenating b with the c. So here in this, these are the particular examples for the data flow. So here like we have one example, b 3 complement 3 dash b 101 and c 3 dash b 111. So here my I'm doing here assign, count and sum. So my sum would be, my output would be 101 111. So I'm just counting and I'm just adding. So here I could say a plus b plus c in. Okay, that is concatenate sum and count. So for example, my a b and this is c, a b, I'm counting 3b 101 and 3b 111. So my output would be 101111. So assign, count and sum. I'm doing here, I'm counting and then I'm adding up. That is concatenate. See, these flower braces are concatenate B with C. So the flower braces, count and sum. This is one example to understand what is a data flow. Coming to the data flow model, this is a model that is a representation, and the syntax wise we will represent. So as it is a combinational logic circuits we can use. For example, this describes output as a function of input. So we describe the output as a function of input. And next, note, the note is use of assign keyword and continuous assignment statements. We see the continuous assignment statement with a word keyword assigning. So if you observe this particular syntax, you see module and gate. Module is a keyword and gate is name of the digital circuits that you are considering, and this is a port list. As I said you before, the port list should contain, the declaration of port list should contain input port, output ports and in-out ports. So in output port should come first and then followed with the input ports. So here this is output port of a primitive must be the first in the port list of ports, isn't it? So this is an important point when you are writing a syntax. Always remember the output port should come first, then followed with the input port. So module, the name of the digital circuits and gate, and the port list consists of output port list first and then followed with the input port list. And you have input, output. Input are in1, in2 and the output is out. And then assign out. As I said you, assign is a keyword that is to be mentioned. So assign out is equals to in, comma, in1, comma, in2. And then finally, we are terminating the particular syntax with the end module. As we have started with the syntax, by calling a word, keyword called module, we are ending up with a keyword called end module. And also important point to be remembered is restrictions does not apply to modules. That means what? Here there is no need to consider only one module. There is no restriction that you have to use only one module, but more than one also you can be used. The module could contain not only one but also many modules can be considered. Module 1, module 2, module 3. Okay, so there is no restrictions, does not apply to this modules. We can consider more number of modules. Coming to the gate level or structural. So what is this gate level talking about? Within the logic level, the characteristics of a system are described by logical links and their timing properties. So in this gate level or the structural, we see the characteristics of a system can be observed, or else the characteristics of a system can be described by logical links and their timing properties. Logical links and then timing properties. With these two constraints, the characteristics of a considered system can be observed. And also all signals are discrete signals. As we don't see any continuous signal, but all the signals are to be in a discrete signal. The signals will be all the signals that are considered is a discrete signal. They can only have definite logical values. As these signals are discrete signals, they have the values. The discrete values, the logical values are 0, 1, don't care and high impedance. So these are the values, these are the values only observed only when the signals are the discrete signals. If they are not discrete signals, we don't find any values like 0, 1, don't care and high impedance. If the signals are discrete, then only we see the output, or else the logical values would be of 0, 1, x and z. Using gate level model might not be a good idea for any level of logical design. So this is a point that for every, as we have seen, there are 4 levels: behavioral, gate level, switch level and circuit level. So there is no restriction that only with this particular model we can achieve the output. Okay, that means what? Only using gate level we cannot, we can achieve the things, but it is not a particular thing that the output can be achieved only using this gate level. We can go for the modeling level, switch level or circuit level. And gate level code is generated by tools like synthesis tools, and the netlist is used for gate level simulation for the backend. So here the synthesis can be carried out using the synthesis tool. In the previous class we have discussed there are some simulation tools. There are some software simulation tools we have discussed. Software simulation tools. They are multisim and mentor graphics. So these are the software simulation tools. Multisim, and the next one is mentor graphics. So in order to synthesize, in order to simulate this gate level code, we have the synthesis tools, and that synthesis tools indeed consist of the netlist, and netlist is used for the gate level simulation for the backend process, and the gate level modeling or the structural. So how the structure of this gate level is, this is how we can see. So in this gate level model, a circuit can be defined by use of logic gates. So as the name indicates, it's a gate level model. We see the circuit can be defined. The circuit can be defined using logic gates, the basic logic gates, AND, OR, NOR, XOR, NOT, NAND and all. So these gates are predefined in Verilog library. Already these gates are predefined in the Verilog library. Already the gates will be present. The gates are present in the Verilog library. So the basic gates and their syntaxes. So this is how the representation of the basic gates followed with their syntaxes. And gate name, input output ports, same. And gate name, it's a gate name and input output ports or NOT, XOR, NOR, NAND and XNOT. So these are the logic gates which are predefined in the Verilog library, and these are the syntaxes. And coming to the structural model. So what is the structural model? Structural model is, it's a composition of primitive gates to form more complex models. So this is a composition of the primitive gate. That means what? You cannot use only one gate, but more than one gates you can use. So it is a composition of the primitive gates. Composition of the primitive gates to form more complex modules. And the important note to be discussed here is, we use while declaration. In the gate flow or else in the gate level module, we have used a keyword called assign, whereas here in this structural model, we are using a while declaration. We are going to declare in the syntax, we are declaring a wire. Okay, so if you observe the syntax, you have module, a keyword, followed with a gate or else followed with the name of the digital circuits. For example, here I have considered XOR gate and followed with the port list. Again I am recollecting, saying that port list consists of output ports. The declaration of the port list, the declaration of the output ports will comes first and then followed with the input ports. And then we have input as A and B and output as out. And here we have via A bar, B bar, T1, T2. Okay, based on the gate that you are considering the wire. See, for example, I am considering AND gate A, B and C. So for this AND gate, this is a wire, B via A, via B and output via C. So likewise, as I am considering the XOR gate, this is a OR gate, this is a XOR gate. So for this XOR gate, A, B and Y. Okay, so Y, A bar, B bar, T1 and T2. So inverter A bar A, inverter B, A bar B, AND gate and 1, T1 A bar, T1 A bar, AND gate 2, T2 B bar and OR gate. OR gate is R1 output port T1 and T2. So XOR is nothing but OR plus NOT, isn't it? Okay, OR plus NOT. OR gate and NOT gate. Combination of OR and NOT is XOR gate. Okay, but the representation, the declaration of wire is the foremost thing to be remembered in this structural model. And finally, we are terminating the syntax with end module. As we have started with the module, we are terminating it with the end module. So what is this structural versus behavioral? So this structural versus behavioral, there are some similarities and some differences we can observe in this structural versus behavioral. So it supports structural and behavioral description and Coming to the structure, in this structure, it is the expressive structure of the circuit, how a module is composed as an interconnection of more primitive modules or components. So here in this structural, as I discussed, not only with one gates we can design the circuit, but also not only with one gate, but also we can design the circuit with more number of primitive gates. See, in the previous example, we have used OR gate. OR ante OR gate. XOR gate. XOR gate is nothing but OR gate plus NOT gate, isn't it? That is XOR gate. So more than 2 we have used. That is a structural model. So it's clearly stating that explicit structure of the circuit, how a module is composed as an interconnection of more primitive modules or components. So it is an interconnection of one or more primitive modules or the structures. Example, each logic gate instantiated and connected to others. So each standard gate or else each logic gate can be connected to others. For example, XOR gate, or else for example NAND gate plus AND plus NOT. So we have AND gate and also we have NOT gate. So this is one gate and this is another gate. So it's an interconnection. It is an interconnection of more primitive modules or components. So the logic gate is instantiated and connected. We will instantiate what are the inputs and what are the output. And also for this particular NOT gate, we will instantiate what is output and what is input. What is output and what is input. So each logic gate is instantiated and connected to others. This is what we observe in this structural. And coming to the behavioral is program describes input-output behavior of the circuit. In this behavioral, the program, it describes about the input behavior and as well as the output behavior of the circuit. So, many structural implementations could have same behavior. So, sometimes what happens is many structural implementations, if you consider different digital circuits, if you will see the similarities. You will see the most common similarities between the two considered digital circuits. So this is what it says is many structural implementations can have some or else many structural implementations have same behavioral structure. Example, different implementations of one Boolean function. So this is one of the example that we can see in the behavioral, that is a different implementations of one Boolean function. So if you consider a logic gate and we represent A dot B, okay, and that the representation is different, and also we see the structure is also different. So the different implementations of one Boolean functions can be observed in this behavioral level. And coming to the modeling types. So how many types of modeling we could see in this Verilog? So the model describes a component in the circuit. Obviously, the model, it describes a component in the circuits. It describes a logical circuit or else a logical gate in the circuit. And there are two ways to describe. So in order to describe this particular component, there are two ways to describe. One is structural Verilog and the second one is a behavioral Verilog. So coming to the structural Verilog, this structural Verilog it consists of list of components, how they are connected. In this structural Verilog, we observe how the components, how the components that are present in the module, how the components that are present in the module are connected. Okay, so we see the list of components and how they are connected. The list of components and the connection. This is what we see in the structural Verilog. And also just like semantics, by using text. So in just like semantic way of representing, we use the text. In the text format, we will represent what are the components are present and how they are connected. And hard to write and hard to decode. As it is a structural Verilog, we have to represent each and every minute component, and we have to represent each and every connection between those minute components. So it is very difficult for us to write the code, and also it is very difficult for us to decode the code. And coming to the last point, it is useful if you don't have integrated designs tools. So it is useful if you don't have integrated design tools. Integrated design tools are nowhere helpful in order to synthesize this structural Verilog. But it is one of the useful if you don't have this particular integrated design tools. We can easily synthesize and simulate. But it is hard to write the code, and it is very difficult to decode the code. Why? Because in the complex, if you consider a complex design, it is very difficult to connect. It is very difficult to connect the interconnections. It is very difficult to interconnect the modules, or interconnect the devices internally, and it is very difficult to point out the each component serially. And coming to the Verilog, behavioral Verilog. This behavioral Verilog, it describes what a component does, but not how it does it. So here it is important point. This behavioral Verilog, it describes what a component does, what it does. For example, AND gate, what this AND gate does, but how it does it, but not how it does it. It describes what, but not how. It describes what is an AND gate, but it doesn't ask about how it describes, how it works out, how it goes on, how it gives the output. It only concentrates on what a component does. Okay, this is observed in the behavioral Verilog. And coming to the second point, synthesize into a circuit that has this behavioral. So it synthesizes the components that you have considered and into a circuit. For example, if you are consider a big complex circuit, it takes out one device, one tiny device, and it synthesizes that particular tiny device into a circuit. So and that has this behavior. So this behavioral modeling is very simple when you compare to the structural model, because this behavioral model, it describes what sort of component, what sort of digital circuit that you are considering, how it what is the component that you are considering. It is mainly focused on, and also it synthesizes that particular that particular tiny device into a circuit. This is all about the behavioral level and the structural level. And this is about the structural model. So this is example for the full adder. Okay, so what is a full adder? Full adder consists of 3 input: A, B, C. A, B, C, C out. Output, input. We have 3 inputs and 1 output. Okay, so here module, name of the digital circuit, that is full adder. A, B, C in output, S and count. S and count. S is the output which it comes from the carry out. That means what? 0, 1. 1 plus 0, 1, and 1 plus 1, 0, carried 1. Okay, so this is the output, carry 1. For example, we'll take 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 0. If you add up these two, 1 plus 1, 0, carry 1. 0 plus 0, 0. 1 plus 0, 1. 1 plus 0, 1. Carry 0. 1 plus 1, 0. Carry 1. 0 plus 0, 0. 1. So 1 plus 0, 1. 1 plus 1, 0. Carry 1. 0 plus 1, 1. 0 plus 1, 1. Okay. So that means what? Here, the carry bit and the output bit. So that is what ABC are in. ABC in are the inputs. S and C out are the outputs. So input ABC in, output S CCount, and assign count and sum. Concatenating of count and sum, which is equals to A plus B plus C in. And we are ending up with the end module. So further, how can we write is module add for A, B, C in, S count. These are the input and the output ports. Input ports we are representing with 3:0. Why? Because 3 input, 1 output. 3:0 A, B, and input C in, and output we get with a combination of 3 input, that is 3:0 into S, and output is C count. And finally, wiring C1, C2, C3. Okay, C1, C2, C3, we are wiring up, that is full adder FA0, 1, 2, 3. So FA0, A0, A0. See, these are the examples that I have given. That means 0, 0, 0, 1, 1, 1, 2, 2, 2, and 3, 3, 3. So these are the full adders. This is a one particular full adder representation for 1, and this is another particular representation of the another full adder F1, and this is another particular representation F2, and this is another particular representation F3. Okay, this is all about a structural module. In this, as I said you before, this structural model is difficult to decode, and it's difficult to write. Okay, they're difficult to write and it's difficult to decode. So this, till this particular, we are calling it as a data flow modeling, and here we are calling it as a structural level. This is a data flow level. In this data flow level, we just represent the data, the gate name, ports, port list, input output port list, sentences followed with the SN keyword, and ending up with the module. Whereas in this structural, each and every point, what are the inputs, what are the outputs, and wiring. See, this is what we have discussed, right? In the structural modeling, module, gate name, input output, wire, and in depth, in detail, how we are concatenating, or else how we are the complex module, how we are declaring the internal part. Internal part can be seen over here in the structural model. The same way we have discussed here in this using example called full adder. So for each and everything, if we are considering 4 full adders, for full adder 1, like how we have to represent full adder 2, 3, and 4. And finally, we are terminating the syntax with the end module. So coming to the modeling styles. So these are this slide is talking about a basic logic gates. You see this is a logic AND function. This is the AND gate, consists of 2 inputs A and B, and this is a Boolean expression A plus B is equals to Y, and these are the truth tables. 0, 0, if both inputs A and B 0, 0, the output is 0, as it is AND 0, 1, the output is 0, 1, 0, output is 0, and 1, 1, output is 1. So A dot B, A plus B, and NAND gate is AND plus NOT, AND plus NOT, NOR, OR plus NOT, XOR, XOR gate, OR plus NOT, XOR gate is 0, 0, 1, 1, whereas OR is 0, 1, 1, 1. So XNOR is AB, AB NOT, which is equals to the NOT. When we give to this XOR gate, it becomes XNOR gate, and these are the truth tables, and this is very important, and these are the basic logic gates followed, like you can remember easily with this slide. What is an AND gate, logic symbol, Boolean expressions, and along with the truth tables. Already in the Verilog, these gates are predefined. They are already in the predefined, in the Verilog libraries, we can find the basic gates. And this is just a difference between a modeling style, in an easy way to understand modeling style, and the behavioral style, the structural behavioral and the model level, behavioral model and the structural model. So this behavioral model, the behavioral model describes the behavioral of the block, whereas in the structural level, it describes the structure, architecture and block parameters. So it is very easy to understand, analyze and also to remember, saying that when you come across the difference between the behavioral level and the structural level, it is important, or else it is easy to remember that in the structural level, you see the structural level, it describes about the structure, architecture and block parameters, whereas in behavioral level, you see this behavioral level, it describes only the behavioral of the block. That is, in behavioral level, need to derive equations for block behavior, whereas in structural level, need to model sub-blocks. We have to come with the sub-blocks, blocks and the main circuit. That means what? If a circuit, composite circuit consists of sub-blocks, 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 we have to come up with the first sub-block 1 and the next sub-block 2, sub-block 3 and sub-block 4. Finally, we have to conclude with the main structure. So, need to model sub-blocks first. And next, more realistic simulation. It is a more realistic simulation, easy to understandable, but it's very difficult to decode the program. Okay. Next, it is need to derive the equation. So, here if you observe this figure, we have ADC, analog to digital circuit, analog to digital converter. If you take, we have analog in, we get analog out with a digital out. This is ADC, analog to digital conversion. We see the analog input can be given, analog output is observed with the analog, the digital output should be observed. Okay, the digital output should be observed with the necessary expressions, or the equations to be carried out. Whereas here in this structural model, you see analog in, you have a buffer gate, whereas that buffer gate is given to the gates, which is where the mechanism will be done over here. That is, we have to get A to D conversion, right? So, analog in means we have to get the digital out. So, in order to get the digital out, it has to meet the connection with one more buffer gate, where here it is segregated, or else here it is expressions can be carried out with the positive and the negative. So in this structural model, you have to sort out this first, and then you have to sort out this next, and finally after the combination, after the combination of these two doing, like we will be observing the digital output. So first is you have to describe the structure, basic structure, and you have to describe the architecture of each and every component, and then you have to describe the block parameters. Okay, what sort of gates are you using, what sort of registers are you using, all the parameters, different timing devices, different timing levels, and all the considerations to be considered in this structural model. So comparing the behavioral and structural model is bit difficult when we compare it with the behavioral model. So this is the end of the presentation. So today we have discussed what are the modeling styles. Data flow, behavioral, structural are the basic modeling styles we have discussed, followed with the examples that we have discussed, the gate, the primitive already, with examples of AND gates and all the basic level gates, and also we have discussed about the syntaxes which are with respect to the behavioral and also with respect to the structural. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.